Hello, Mr. Runo, Mr. Runo. Gonna double check that. If you could see it on the board. Nope. Alright. Light test. Kinda, yeah. Not the best chalk for this. Hello, Mr. Runo. I see you. Alright, so what I have is a metric E times Hawking radiation to the natural logarithm 1/2, and that would be denoted as the 1. So if you were to take a circumference of a black hole, you would have theoretically multiple of these, but it needs to be finite. So from a limit of however many, you would need to have a certain amount, because if there were infinite many, then you would have a collapsing black hole. So there has to be some dynamic between here, where the asymptote E is equivalent to a mechanic which limits it. So I have an already preset equation where I say E is a join with a number n over the circumference. So circumference of a circle would be 2 pi r, and I don't know what the volume for a sphere would be as a black hole. I'm sure it's just 2 pi r. I'd have to look into that. Obviously, if I make mistakes, then that's alright, because it's just for fun. So I have 2 pi r, and so if S equals Hawking radiation A times C to the third, or cubed, over 4 Planck scale, metric, I forget what it is, times gravity, then this would be a combination of the equations. So then you would have so if this is singularity here, then you have a limit of some mass to, let's call this, you know what, U for the singularity, just for cases of not confusing it with any other variable. So a limit of m to u must contain a finite amount of asymptotes, because the idea, the hypothesis, which I don't have enough space on the board to write, is that if there are an infinite amount, there also has to be infinite entropy, and also infinite, possibly any aspect or variable that makes up the black hole. So If you have an asymptote on the horizon, something that is fed into the black hole, then it would go maybe something like an excitation. So the way I notate excitations is I go E-I-M. So an excitation in an imaginary space, which is because of the curvature of a black hole on the outside, and the mass of it is notated as the subscript. So that, with a little map set sign in there for general purpose, the excitation map sets to the limit of the mass du. So this is where it gets confusing, because if you have a particle that's entering, you can't have infinite entropy. So I think it's either S or T that's denoted as entropy. I'm pretty sure it's S, relating to Hawking radiation, as I possibly mistook Hawking radiation for being equivalent in some way to entropy. So there we have that, and makes me wonder if, in relational calculus, a not so studied field, A would be relative to B. So A relational B is equivalent to B relational A, but A does not equal B, just as B does not equal A. So if you have a collapsing black hole, then it would be a case where it's possible the black hole is unstable, so just a general Einstein-Rosen bridge. So Einstein-Rosen bridge. And not one of the Morris-Thorne wormholes. So not Morris-Thorne. So not Morris-Thorne wormhole. There would be collection of information on the outside. So information is different, and entropy is finite. So finite entropy means that if this is correct, Stephen Hawking's radiation, or Hawking radiation, that is, then that must mean if coupled to the asymptote E for this space, then it would have similar aspects to Hawking radiation, which is what I'm trying to prove. Here's the board. Boop boop, cleaning the board, yeah! With my asymptotic relationships in relational calculus between homological topological fields, yeah, of A to B, yeah, yeah, ooh yeah, clean.